This is the second lesson for Unit 7. In Unit 7 we're doing accumulator problems, and in this particular lesson we're just going to go through 5 examples of different things that you could be integrating to come up with some accumulation to come up with your desired answer. This first story is kind of an old story. It's a physics story. We've done questions like this before. Just kind of want to show you that it fits into the context of this chapter. It says the velocity in meters per second of a particle is given by this function here, 6 sine of 3t, and that's good all the way out to pi over 2 to 90 degrees. Part A says figure out when the particle is moving to the right, or when it's moving to the left, or when it's stopped. Okay, sure, yeah, we can do that. I'm going to start off by actually looking at when it's stopped, trying to figure out when that velocity is equal to 0. So they've told me that the velocity is 6 times the sine of 3t. And I'm wondering, hey, well, when would that actually be equal to 0, right? So putting in a velocity of 0, forcing that to be 0, yeah, I can figure out when this particle is stopped. Well, if I divide by 6, I find out that the sine of 3t has to be 0. And I'm kind of wondering, well, what are my options here for t for doing that? Again, I always just think about, when I do my special angles, I always just think about a kid riding on a Ferris wheel, you know, the unit circle. And sine is all about y values. And I want to know when is the y value 0? Well, that would be like there and there. And as many times as you want, driving this thing, driving the Ferris wheel around again and again and again and again. So for me, I'm looking at it saying, you know, this 3t, this angle inside there, that would have to be 0 or pi or 2 pi or 3 pi or 4 pi and so on, just all the way down the road. Well, now I'm going to go and divide that by 3 because it was 3t that had to equal that. Well, 0 divided by 3 is still 0. This would be pi over 3, which is less than pi over 2. And then when I divide this one by 3, I would have 2 pi all over 3. And by then you're already too big. And then 3 pi divided by 3, that would just be a pi, and so on. But we've gone past this pi over 2 already. That one's too big, and that one's too big, and all the other ones are too big. So really, there are only 2 moments that we're looking at where this thing is stopped. And that's at time 0 and at time pi over 3. So as always, I'm going to set myself up a nice little interval table, and I'm going to slice up my timeline at 0 and pi over 3, and then I've got my endpoint there at pi over 2. Okay, so time intervals. I do have an interesting moment right at 0. We begin stopped, and then we're going to look at all the times that are in between 0 and pi over 3. And then pi over 3 is an interesting moment because the particle has no velocity. It's going to be stopped. Velocity will be 0. And then there's all the time from pi over 3 out to pi over 2, and that's when we're supposed to stop this story. Okay, so let's go and examine 2 different things. Let's go and talk about, first of all, what they've given me, which is velocity. And then we can talk about, well, what's the position doing? What's the story doing? Well, the velocity is 0 at time 0, and it's also 0 at pi over 3. And now what you do is you go and you grab times that are in between 0 and pi over 3, any number you want, and you test them in this story, 6 sine of 3t, and you see what you get. And I found that when I picked a time in here, that I found the velocity was positive. So we're increasing our position, right? We're moving forward. So this would be a time when your object is moving to the right. And when I checked out a time in this time interval, I just picked one, I tried the velocity out, I found that velocity was negative. Okay, so we're moving backwards. We must be moving back to the left. And we were stopped here, and we were actually stopped at the very beginning. So we begin stopped, we start with a positive velocity moving to the right, then we stop, and then we move back to the left, and then the story is over. Okay, so part A is done, and then B and C, they ask for the displacement and the distance during that time period. And in many ways, that's kind of like doing that, issue with the span. Like, do we want to be looking at like the actual position, in which case we need to know where we started, or do we just want difference in position? So I know we put that on the front cover here. I'm not going to do the second option here. I just want to do this first one, the change in position, if I want to do displacement. And then distance is a whole new game. You have to look at integrating speed. So yeah, let's do it. Let's do a little bit of integrating here, a little bit of accumulating. For B, if you want to know displacement, so this is really nothing new to us. Displacement is equal to the change in position. So it's actually going to be just the integral of the velocity, dt. That's all we have to do. So I would be integrating from 0 to pi over 2, because they said do it for the whole time. And I would be integrating 6 sine of 3t dt. Now, a lot of the times in this chapter especially, we're just going to say, hey, go to your calculator, find out what that integral is. There's nothing wrong with that. This one, though, maybe I'll just do this one. It's kind of good review. If I was doing an antiderivative of this, personally, here's what I do. I don't try to get it perfect right away. I would say, well, I know that sine and cosine just kind of flip-flop back and forth. Sometimes there's a negative, sometimes there isn't. So I begin by writing that down. I'm like, I bet you it'll look roughly like that. And then I start thinking, if I took a derivative, would I end up with what I want? And the answer is no. If you took a derivative, you'd actually pick up a negative sign. So I'm going to put a negative in there, just a little preemptive negative. That way when the negative shows up from doing the derivative of cos, it'll go away. I would also pick up a 3. And I kind of want to see a 6 here. So I kind of have to have a little 1/3 bodyguard, and then the 6, that's just going to reduce down to a 2. So overall, I've got a negative. That way the cosine can turn into a sine. And a 2 would be just perfect. That way when the 3 arrives from the chain rule, I'll end up with that positive 6. And I would evaluate at 0 and at pi over 2 just to see what I would get. And when I tried that out, what I found is when I put in pi over 2 into that, I ended up getting nothing out, just a big 0. And then when I put 0 in, I ended up getting a negative 2 out. And so it looks like the displacement for this thing is equal to 2 meters. So it actually goes forward a fair bit and then backs up, and overall it's only displaced by 2. Now the final question, I think I can still squeeze it in. Final question says, yeah, but how much did you wear out your shoes? What kind of distance did you cover? Well, that is going to involve integrating as well, but this time I'm going to integrate speed. So distance is going to be the integral of speed dt. So I would go to my calculator and I would say, hey, calculator, I need you to help me out. Can you integrate from 0 to pi over 2? And I need you to do the absolute value of this velocity. This velocity was 6 sine of 3t dt. And just let your calculator have it. There's nothing wrong with that. And it ends up being a lot more than the 2 meters. It ends up being 6 meters. So just looking at the story, I know it went forward, stopped, and then backed up for a bit. It must have gone forward 4 and then backed up 2. That way the distance was 6, but overall it had only covered 2 meters. So yeah, an old story, but also appropriate for this chapter because we're integrating things in order to accumulate up to the final answer. Okay, let's go and take a look at our next question here. Oh, it's an electricity question. The rate at which your home consumes electricity is measured in kilowatts. Okay, great. If your home consumes electricity at a rate of 1 kilowatt for 1 hour, you'll be charged 1 kilowatt hour. Okay, that's the amount of electricity that you use. Suppose that the average consumption rate for a certain home is given by this function here. Some weird complicated thing, 3.9 minus this 2.4 sine of pi t over 12. Okay, whatever. Where C is measured in kilowatts, that's your consumption, and T is the, C is the not the consumption. C is going to be this consumption rate measured in kilowatts, and then T is in hours, starting at midnight. And you have to find the total consumption for the home measured in kilowatt hours. So this is the rate of consumption here. Maybe it should have been called an R instead of C. Right? So this is a rate. And they want to know how much we're actually going to use in one day during this story. So you've got kind of a couple of options here, thinking about the very first thing we wrote down on the first page there about, do you want to do spam or do you not want to do spam? If you do change in amount, then all you have to do is just integrate rate, dt. If you want to know the amount total ever used in your house, ever, you'd have to say, well, how much did I use up until this day that I'm about to look at, and then add on this one day. Well, I don't really want to find the total amount of electricity that I've used ever since the beginning of time. So I don't really want to do this spam option, right? That's not what I want to do. I just want to find out how much more electricity I've used in that one day. Okay, yeah, so here we go. The additional amount of energy that gets used, it's just going to be the integral of the consumption rate. So I'm going to integrate this 3.9 minus 2.4 sine of pi over 12 times t dt. You absolutely could just ask your calculator to do this. We're going to go for one day from 0 to 24 hours later. There's nothing wrong with getting your calculator to do it. If you dare, you could do it by hand. It's not actually that bad. The antiderivative, it's going to be 3.9t for the first part. Yeah, okay, that part was easy. Now the next part, don't try to get it perfect right away. Just sit there and go, well, you know what? It's probably going to have a cosine in it. Right? There's probably going to be a cosine of pi over 12t. And then you start looking at it and you go, okay, well, what would happen if I took a derivative? The cosine would turn into a minus sign. Oh, how perfect. There's a negative there. So I'm happy with this being a plus story. But then the chain rule would kick out a pi over 12. And if I don't want to see a pi over 12 out here, I might need to include a little 12 over pi bodyguard. And then the 2.4 just hangs around. So you'd have a 2.4 and then a little corrective 12 over pi sitting right there. And now we could just go and evaluate. Final number is 24, the initial number is 0, and we'll do final minus initial. And you could have just gone to your calculator and just said, calculator, just do this, please. And either way, we're going to end up with the answer, which is 93. Well, if it's 93, I should write 93. 93.6 kilowatt hours. Okay, 2 down, 3 to go. This next one is a challenge. It's probably the first time you're going to have seen one that looks this interesting. And once we kind of figure out how to literally cut this problem up, it'll actually be okay. So it says a slab of metal measures 12 centimeters across. Yeah, okay, I can see that down here. There's the 12. 8 centimeters tall. Yep, okay, great. And 2 centimeters thick. Okay, so that I guess means that, looking this way, that's a 2. Okay, great. Although the dimensions are nice and regular, it's just a nice little brick shape, the density in grams per centimeter cubed of the metal varies throughout the slab. Oh yeah, it's kind of like the shading here, right? It's like more dense here on the left side, less dense on the right. According to some density function, that will tell you the density at any spot you want to check, right? And it's equal to 4 on top of x plus 8. And you have to try to find the total mass of this slab. Whoa, that's a challenge. So trying to think of just like, physics and chemistry, I think generally the idea is that density is supposed to be mass divided by volume. But all the easy ones we did in physics or chemistry, we always had a nice consistent density. Now the density is changing, and I'm trying to find mass. So if I spin this story around, mass should be density multiplied by volume. But my problem is it's not always the same density as I look at the material. I do notice that this density formula does not have any y's in it. So it doesn't seem to depend on whether you're checking here or here or here or here or here. In fact, the shading on this picture looks all the same in that area. But it does matter when you change your x's and you start moving that way. So that's kind of an interesting little thing to note, that really this density is only a function of x. What I want to do, the first step in these problems, is I really just want to look at the symmetry of the problem, okay? And spend a moment, don't rush this part, just look for some nice symmetry. And again, what we noticed a second ago is that, yeah, it's actually got the same density up and down. It's just not got the same density left and right. Another way to think about this little step here that I've mentioned is you have to sit there and kind of ponder this thought. You have to imagine how we should cut the slab. And I'll put cut in kind of air quotes here. We're going to mathematically cut this slab of metal into some small little shapes. And I've noticed that it's beautifully consistent in density up and down. So I want to imagine taking like a little calculus scalpel and coming in and slicing up this chunk of metal into a whole bunch of little thin little pieces of toast that look like this. Just a whole bunch of little rectangular prisms. If I cut it like that, actually I'm going to just draw that again. It's not totally clear. I didn't do a great job there. If I can make just a small little cut in here like this, that's a bit better. Then that little slab of material, if I cut it super thin, it's going to have one value for density. And what I'm going to do is I'm going to let x talk about my location along the x-axis, and then dx is going to be some small little microscopic change in the x values as I walk across that x-axis. All right, step 2. This is where it gets interesting. Don't try to memorize formulas for every specific situation. Instead, just you take a nice relaxing breath and you say, okay, I want to remember that the calculus works for me. Not the other way around. You're not a slave to the calculus. It has to do what you want it to do. So you can sit here and go, okay, how can I get it to work for me? I want it to go and add up all these little densities, or all these little masses for all these little slabs of metal, and they each have their own density to them. So don't try to, again, memorize some calculus formula for some specialized integral. Instead, you can sit there and go, well, let's look at one of these little pieces of metal toast, one of these little slabs. Let's start thinking about its dimensions. It's going to be 2 centimeters that way, 8 centimeters that way, and these are very, very, very thin. I want to cut them so thin that people won't notice that the density is changing. And if they notice that, oh, hey, look, it's a little more dense on the left side, just cut it thinner. So dx is going to talk about how wide that slab is. Now what I know is that generally speaking, mass is equal to density multiplied by volume. So let's go and think about what the mass would be for this tiny little piece right here. What's its mass? It'll be very tiny. I'm going to call it a dm, right? Small little tiny mass. Well, it's going to be the density multiplied by the volume. The density for that particular slab depends on where it's located. The density function was 4 all on top of x plus 8 because they said so. Okay, so there's the density, right? That's just this part of the formula right there. And now I have to multiply that by the volume of this little tiny piece of toast, little metallic piece of toast. That's going to be 8 times 2 times dx. Right? Dx is how thin that little slab is. And now here comes the part where I say, calculus, you're up. You got to do this job. And I'm going to say, okay, the actual total mass for this whole thing, it's just going to be the sum of little masses. Just take all the little masses and just add them up. It is going to be nothing but the integral of dm's. But the dm's, the little tiny mass, little elements there, they're given by that expression there. So, okay, here we go. The total mass is going to be an integral going from the very beginning of the slab to the end of the slab, and it's the integral of this. All I'm writing down right now are the little tiny, super small little bits of mass that I'm going to add up. Now, where does the first mass start and where does the last mass end? The first mass in the picture would begin down here at x is equal to 0 and finishes up here at x is equal to 12. So I'm going to put in my integral. Yeah, please start at 0 and please finish up that last little mass element at 12. And just thinking about it that way, it automatically picks up the little dx in the equation, and I'm totally ready to go. I would probably just let my calculator do this, although we could do it by hand if we had to, right? So we're integrating from 0 to 12. Looks like we've got 8 times 4 times 2, 8. Oh, that's like 64, all on top of x plus 8 dx. Technically, that's an integration by substitution, but I kind of know how this thing's going to fall apart. The 64 is going to hang around, and then we're going to have a ln of x plus 8. I don't really need to put absolute value bars on that because I'm going to go from 0 to 12. And when I go 0 to 12, when I add 8 to that, I will have no negative problems at all. And now I would need to go to my calculator to evaluate this, and it's 58.6426. So I just kind of thought about it in small little elements, small little pieces, and then said, hey, calculus, you've got to go and add all that up. When it was time to do the integral, I can either do it by hand analytically, like I've done here, in which case I could just take the 12 and the 0 and substitute in. So basically I said, okay, what is 64 ln of 20, when I add the 8, minus 64 times the ln of 8. And there was the 58.6426. The other option would have been to say, hey, calculator, you've got to do this. Okay, you've got to go and do this integral. I wouldn't do any antiderivative then. I would have just said, okay, calculator, I need you to go and integrate for me. It's 64 divided by x plus an 8, and I'm using x's from 0 to 12. So I don't do the antiderivative if I'm going to get the calculator to go and do it for me. All right, third one's done. This next one, I'm going to have to show you a little physics explanation for how to do this calculation, but then the calculus is not too bad. Oil flows through a cylindrical pipe of radius 3 inches, but the friction from the pipe slows the flow towards the outer edge. So yeah, this happens when you have fluids flowing through pipes. It's actually the very center of the pipe that has the fastest flow. The speed at which the oil flows at a distance r inches from the center is given by some flow rate. Okay, complicated looking thing. Set up and evaluate the integral that will give the rate at which the oil is flowing through the pipe. All right, well, here's a little physics story, a little background information that it's totally fair if you didn't know. If I have some sort of duct for having, maybe it's like air or water, anything like that to go through, I'm going to make this one rectangular just so it's a little easier to think about. So here's a little rectangular pipe, and we're going to have something flow out of it. Could be a heating duct in your house. And let's say that the dimensions for the duct are 2 inches tall and 5 inches across. And imagine that water or air or anything is flowing out of there with a velocity of, oh, I don't know, let's say 4 inches per second. You can actually find the overall flow. This is what we do in physics by multiplying the area by the velocity. Let's make this a full equals here. So you could just take the area, which would be 2 times 5, and then multiply by the 4. And what do we get? We'd have 40. And so you could say, oh yeah, I've got 40 inches cubed per second. And that's going to tell you your flow rate. Well, that's great if it's a nice, beautiful rectangular pipe. And if every part of that area has fluid flowing out of there at 4 inches per second. But our story apparently is different. Okay, according to what they're saying, when stuff comes out of this pipe, it's actually flowing at different speeds depending on where you look at it. So I'm just going to draw a little pipe here. Okay, so there's my pipe. And some oil is going to flow out of here. But what we'll find is we actually have different flow rates depending on where you check. So this pipe has a radius of 3 inches, and if I check right in the center, right here, where the R value, the radius for that spot would be 0, if I put 0 into this, 10 minus 0 is 10, times 8 is 80. What you'll find is right here in the center, the oil is going to flow very fast. It's going to flow out at 80 inches per second. But if I move away from center by a little bit, if I go out here 1 inch from center, okay, where the R is equal to 1, so we've got R equals 0 right here. Here's R is equal to 1. Okay, you put 1 in. 10 minus 1 squared is a 9, times 8 is 72. Okay, oil right there flows out a little bit slower, not much slower, just a little bit slower, 72 inches per second. Still impressively quick. If I move a little farther from center, let's go to here at R is equal to 2. If you're 2 inches away, 10 minus 2 squared, 10 minus 4 is a 6, times the 8 is 48. Okay, it's slowing down as we get near the edge. And then right at the edge, right here, when R is equal to 3, 10 minus 3 squared, 10 minus 9 is a 1, times the 8 is an 8. Whoa, look how slow it is right there at the edge. Barely moving at all here. 8 inches per second. That's the velocity there. So it's going to be a little more interesting than the nice picture over there on the left. What we have to do is try to find a way to cut this story up into nice little sections where we can say, wow, on this part of the pipe, the flow is all the same. But it doesn't work to like slice the pipe like this, because you can't say that all along there the flow is the same, because you'd be closer to the edge at one point. So slicing that way is not a good way to work with the symmetry of the problem. And slicing this way doesn't work well either. You can't say, oh yeah, just look at the flow all along here, because it would be more in the center, slow at the edge. So what we do, you have to get a little creative here. You have to think about like slicing it in little rings like this. You have to say, well, what about a little ring of pipe area It's like right around here. That whole ring has the exact same flow rate in it all along there. So that's going to be my plan. I'm going to work with little tiny little onion rings and see if I can figure out what this answer is going to be. I want to tear that little picture apart a little bit more because it's hard to get all the variables into that. So I'm just going to draw that again just over here. This is the face of the pipe. And let's go and look at a couple of little rings that are in there. Okay, just from there to there. We'll just do a small little ring. That way if somebody's like, oh, I noticed it was flowing faster near the edge, you can say, oh, give me a second, I'll just cut it smaller. So we're going to say that that particular ring is located some distance r away from the center. So r, we'll talk about this distance. But then the thickness of the ring, this is just going to be dr. Just a small little change in the r. Okay, I think it's time to go and do this integral. Our overall amount of flow, I'm going to have to go and integrate a whole bunch of small little flows. I'm going to just add up each flow from each little onion ring there. Okay, so the overall flow is going to be a sum of, now I just have to go and think about how much flow would I get from just this little section of the pipe. It's got a small little area to it, and then there's some velocity there. Well, for a moment, let's think about exactly how much area there is in that little ring. It's kind of like a sidewalk, just a little circular sidewalk. And so the area, it's actually just going to be the distance around multiplied by the thickness of the sidewalk. So it's a circumference of 2 pi r. That's how far it is to walk around this little sidewalk, multiplied by how wide the sidewalk is. That would be dr. Okay, here we go. When I go to add up these small little flows, those flows are just going to be areas multiplied by velocities. Well, the area, it's going to be what I have there in orange. It's going to be 2 pi r times dr. That's how much area there is highlighted there in blue. If that's troubling for you, I know the first time I saw that I was like, what is going on? Imagine you take this little blue sidewalk here and just kind of unwrap it a little bit. Okay, kind of picture it like this. I know it's curved, but you can think about it being like a kind of a wrapped around rectangle, and its distance this way is just the circumference of the circle, 2 pi r. And then you have to think about, well, how thick is this sidewalk? Well, that's just some small little change in r that we're doing. That's the dr. Okay, well, that's the area, 2 pi r times dr. And then the velocity, well, they told me, they said that the velocity was going to be 8 times 10 minus r squared. Okay, well, I'm going to rearrange that a little bit just to make it look nicer, and then we'll be ready to go. So this is going to be an integral. I'm going to put the dr way down here at the back end. It just looks nicer back there. And what else have we got? There's a 2 and an 8. Okay, so that's 16, and there's a pi. Okay, so 16 pi. And then there's still an r. And then there's this 10 minus r squared. Oh, I don't want to try to do any kind of product rule. That would be integration by parts. That's not fun. Let's go and package that all together. So this is going to be an integral of 16 pi. That's pretty innocent. I can slide the 16 pi right out of the integral sign. And then in here I'm going to have 10r minus r cubed dr. Now the integral has to start and stop somewhere, and the r is in charge. It tells me where we're going to begin and where we're going to end. And the very first r, the very first little ring, starts at radius 0, and the last r finishes at radius 3. So I'm going to put in here from 0 to 3. So to decide what to put in for those, just look at this dr. That's in charge, and it says let's finish at 3, let's start at 0. And now you just go to your calculator and you say, hey calculator, I got a good integral for you. Right? In this chapter, we're not so focused on doing those integrals by hand. Instead, it's more about getting them set up. And there, the setup is done. Now you could go to your calculator and say, what is it? As a decimal, it's around 1244, decimal 0706. And the units here are going to be inches cubed per second. Which takes us to our final question of the day. It says a machine fills milk cartons with milk at approximately a constant rate, but backups along the assembly line cause some variation. The rates, measured in hundreds of cases per hour, so when it says 120, it's actually 120 multiplied by 100, are recorded at several times from 8 until 6. Okay, great. Use the trapezoid rule to determine approximately how many cases of milk were filled during that 10-hour period. Well, I do have to decide which deal I want to use, right? Do I want to go change in amount would be just the integral of rate dt, or am I trying to do hey, the amount at time 2 is the amount at time 1 plus the integral of rate dt. Turns out I don't want that one. That would allow you to figure out, hey, what's the total amount of cartons of milk our company has ever made, right? Well, we'd have to say, well, how many did you make up until the beginning of the day and then out on the new stuff for the day? I just want to know how much new stuff, how many new cartons did we fill in one day? So I'm just going to integrate the rate in order to find the amount. That's my plan. Now the story here, it doesn't have a graph, but I'm just going to just pencil one in. So I've got rate here, and if I integrate that, I can find the change in the amount. And then time is going along this axis. But be careful, they haven't got even jumps of time. The first fence post here is actually at 8, and then 9, and then 10. Oh, and then a bigger jump. Then we jump to 12. And then a small jump to 1, and then a big jump to 4. I need a little more room here. And then a small jump to 5, and then a small jump to 6. So just looking at how big these spans are, these little fence runs, well, this is a space of 1, space of 1, space of 2, space of 1, space of 3, and then space of 1, space of 1. Just looking at the widths for all these little stories here. Okay, it says use a trapezoid rule to estimate how many cases of milk were filled. Okay, well, trapezoid rule, I know one way that I can do that is I could do a left rectangular method, a right rectangular method, and then just average. That's going to be my plan. So for the left one, let's do our left approximation. We're going to be attaching all of our little ribbons on their left side. So this first ribbon, when you're trying to figure out like, well, where would it get attached? That ribbon there, if you attach it over on its left side, then when you go to look at the table, you'd be saying, oh, okay, if I attach it on its left side, I'd want to make sure that this point right there is hooking up with that 120 number. And you would continue that pattern all the way through your calculations. So you would say, okay, the change in the amount, according to the left approximation, the change in the amount would be 120 tall and 1 hour wide, plus 110 tall times, that would be 1 hour wide, plus 115 tall, but that span would be 2 hours wide. And then 119 tall, and that one would only be 1 hour wide. And then the next one here from 1 to 4, picking up at the beginning of the integral, the left side, you'd have a 120 for 3 hours. And then a 112 for 1, and then a 110 for 1. And I would not use that last fence post. And when I use that approximation, the left approximation, the number I get is 1,161. Now remember, these are hundreds of cases. Well, we're trying to do trapezoid, and we're getting there by doing a left and a right. So we've got to finish this off with the right. So how many new cases did our company produce? What's the change in the amount that our company has ever done? Well, now I'm going to be going and attaching all the ribbons on the right-hand side. So I want to be looking for the Y value here for each one of these intervals. So my first fence post to grab is actually the 110, and then I'm going to follow that pattern. So it would be 110 fence post for 1 hour, and then 115 for 1 hour. But the next interval is too long, so be careful with this one. It's going to be 119 for 2 hours. Let's just look at the table and see where that's happening. It's from 10 to 12. It's right in here. And I'm doing a right attachment, right attaching on the right-hand side. So 2 hour span, the right attachment's 119 high. Okay, continuing on with the pattern, I'd have a 120 for 1 hour, 112 for 3 hours, right? That's this little run in here from 1 to 4, attaching on that right-hand side. And then a 110 for 1 hour and a 121 for 1 hour. And using that right attachment, my estimate for the change in the amount of cases that our company has ever made is 1,031. Again, those are hundreds of cases. Okay, trapezoid. All I have to do now is just average those. So I'm going to take 1,161, add on 1,031. I'm going to take those two numbers, add them up, and then divide by 2. And I end up with 1,096. Again, though, those would be hundreds of cases, because that's what they had in the table. Okay, well, maybe it'd be nice to just write that out as a nice reasonable number here. We'll add a couple of zeros. So on this one day, your company is going to add to its total number of milk cartons it's ever filled by this many. Okay, it'll be that many cases of milk, that many cartons of milk. Now, how many cases or cartons has your company made ever since the beginning of time? I have no idea. I need to know how many you made up till yesterday. But on that one day, that's how many new ones we're going to add. So yeah, we're just integrating rate in order to find them out.